Okay, so good morning, everybody. Now let's come to the most important part of this chapter, the derivations for Rn, the radius of the nth orbit, then the kinetic energy of electron, then potential energy, and then we would have an expression for the total energy also, En. And this is what we are going to calculate using uh, Bohr's second postulate of constant angular momentum. Okay, so let's start with the basic consideration here that the nucleus having this much positive charge is attracting an electron at a distance of Rn with a force F, which is the centripetal force. So this Fc is my centripetal force, which in this case is 1 by 4 pi epsilon naught into Q1, that is Ze, into Q2, that is E, upon R square, Rn square. This is the radius of the orbit, or you can say the distance between the two charged particles. Here's the electron. Now the centripetal force would be mv square upon Rn, right? As per your understanding of class 11th, this is how it goes. So when I'll just cancel this Rn from this, I get one single Rn here. So on Rn, this is the expression that I've got. Okay. Now what I can do is I can get one expression for kinetic energy here, which is half mv square. So it gives me half into 1 by 4 pi epsilon naught Ze square by Rn. So this is my first equation. Then potential energy can be K Q1 Q2 by R. Now K is 1 by 4 pi epsilon naught here. Q1 is Ze. Q2 is minus E, positive and negative. Here the sign is important. And then there is Rn here. So this gives me minus Ze square upon 4 pi epsilon naught Rn. This is my second expression. Now if somebody asks me the total energy would be K plus Pe, and when we'll add them, we'll get 1 by 8 pi epsilon naught Rn Ze square minus Ze square 4 pi epsilon naught Rn. This gives Ze square upon 8 pi epsilon naught Rn, and then there is a minus sign here. So this gives me total energy En. I can write this as 3. Now the thing is that I have to find this expression Rn, and for that I'll be using second postulate of Bohr's experiment. So let's use that. Bohr's postulate, second postulate, was that mv_Rn is equal to nh upon 2 pi. That the angular momentum of an electron moving in nth orbit is always an integral multiple of h upon 2 pi. So based on that, what I can do is I can substitute the value of Rn. I can substitute the value of Rn as a nh upon 2 pi mv. Yes. So when I do that, if I do this thing, what I get is this Rn is this, and I had this another expression, which is this. Let me call this as A. So let's substitute it in this way, because I have to find the expression for Rn, so I'll be substituting for V rather than Rn. So I'll put it as nh 2 pi m Rn. This would be the expression. So let me call this as 4. substituting 4 in A. So this gives me m n square h square 4 pi square m square rn square. And on the other side I have 1 by 4 pi epsilon naught z e square rn. So I can cancel out things. This gives me rn here. So if I have to find rn, what it will be? What it would be? It would be m n square h square 4 pi epsilon naught z e square, then this 4 pi square m square. 1 m can cancel out from here, then this pi, so only pi is left here, 4 can be cancelled out. I get n square h square epsilon naught upon z e square pi m rn. Now for hydrogen atom, z is equal to 1, so r n would be n square h square epsilon naught pi m e square. So this is an expression, and if I'll further study it, I'll find this as 52.9 n square picometer. Picometer means 10 to the power 9 L 12. So this much meter is the radius of the nth orbit. So you can see this Rn has this n square proportionality. So as it goes, simple derivation. Yeah. So we found Rn here. Now with this Rn I can get Ke and Pe also, and total energy also. So let's find it out. Kinetic energy expression that we got earlier was this. This is half into 1 by 4 pi epsilon naught into Ze square by n square, by Rn. And I know that for hydrogen atom I'm taking Z as 1. So it's half into 1 by 4 pi epsilon naught. Z is 1, E square is there. At the place of Rn I'm going to write what I just derived. It was n square h square epsilon naught. I think this was the case. Yeah, you can see n square h square epsilon naught upon pi m e square. So let's substitute this. N square h square epsilon naught, and the numerator it will be pi m epsilon naught, pi m e square. So I got e square here. So what I can do is I can do the calculation this way, that it gives me me4 pi me4 upon 8 pi epsilon naught square n square h square. I can cancel this out. This gives me me4 8 epsilon naught square n square h square. This is the new expression of kinetic energy that I'm getting for hydrogen atom. So this is, now we can call this as 5. Next is the expression for potential energy. It was earlier given as this, minus Ze square by 4 pi epsilon naught Rn. You can see I substituted it here. So it goes like minus, then this is 1 E square 4 pi epsilon naught. At the place of Rn it would be n square h square epsilon naught. In the denominator pi m e square. So again I get the expression as, I can cancel this out, pi and pi. This gives me me4 m to the power me to the power 4 then 4 n square h square epsilon naught square also. So this is the expression for potential energy that we have got. You can call this as sixth. Now the total energy would be energy of electron in nth orbit, En. It would be kinetic energy plus potential energy. Let's add them. Me4 8 epsilon naught square n square h square minus Me4 4 n square h square epsilon naught square. This gives me Me4 8 epsilon naught square n square h square, which is in minus, and if I do the calculation, I get it as minus 13.6 by n square eV. This is the energy in the nth orbit, right? You can see. So En has this n square proportionality. If you do it for another hydrogen-like atom with different atomic number, then you would have to mention this 13.6 n square, and z square is also here. But in case of hydrogen atom, it's minus 13.6 by n square eV. eV is electron volt. 1 electron volt means 1.6 into 10 to the power minus 19 volt of energy, which you know is work done per unit charge. So it's like, and when you'll do it, it's joule per coulomb. I believe this E is for 1 coulomb, then joule per coulomb. Like if you'll have 1 coulomb here and you'll put the values 1 joule per coulomb and 1 coulomb here, the coulomb cancels out and you get 1.6 into 10 to the power minus 19 joule. So this is the expression for total energy that we just got. So now with this, you can always predict what frequencies would be emitted when the electron moves from one energy level to another energy level. So if I make the energy levels of electron, let's say this is n equal to 1, then we can have other energy levels as n equal to 2, and further you can go for other energy levels, yeah, and this can go to like this outermost level, which is the farthermost point. Now the thing is that as the electron moves from one energy level to another, it releases energy, okay? And for hydrogen atom only, we have found that whenever electrons fall from outermost shell to n equal to 1 level, they emit photons, and these photons have certain wavelengths. The set of those certain wavelengths is called as Lyman series. Like final orbit wherever the electron would fall is always 1. This is the case for Lyman series. The second case is whenever electron falls from any orbit, any upper orbit, to n equal to 2, second orbit, then that series is called as Balmer series. Then similarly, if electron comes from any higher energy level to the third energy level, then again it emits photons of certain wavelengths, and that series is called as Paschen series. These are the names of people who have worked upon them and invented them. That way we have reached to n equal to 3 level. Then we have this fourth series, which is from any energy level to n equal to 4th level. So this this series of wavelengths is called as the bracket series. And this last one, though we can define many more, but for your course I would suggest only till n equal to 5 is fine for you. So n equal to 5, this is p fin series. So whenever the electron would go from higher energy level to n equal to 1 energy level, then it would emit wavelengths which would come in the Lyman series. Then when electron would move from n equal to from any level to n equal to 2 level, then it would emit wavelengths in the series which is called as Balmer series. Then similarly, for third level, this n equal to 3 level, it is Paschen series. For this n equal to 4th level, it's your bracket series. And for n equal to 5 level, it's the Paschen series. So this is what we all have to keep in our mind. All these higher energy levels are called as, see, n equal to 1 is my ground state. But the other energy levels, whenever electron rises from one energy level to other energy level, these further can be called as your excited states. And when electron would cross this outermost level, or I would say would move out, then it would get ionized atom, because the electron has left, outermost electron has left. And that is called as an ionized atom, and the amount of energy required in that case is called as my ionization energy. And then there is this for Balmer series, we have this visible region. We are able to see colors. See, it's I'll put this up again after a while, but for different regions, we have different EM waves coming out. The photons that would be coming out, they all have the certain wavelengths. Okay, so to get that wavelength, what is the formula that I used? As per this Bohr's third postulate, which is E initial minus E final. I'm considering that electron falls from higher energy level to lower energy level. So let's say if it is this like this, so it would be minus 13.6 upon Ni square minus 13.6 upon N final square. This is the photon, this basically the energy that is emitted, and this emitted energy will always be in the form of packets of energy, and where each packet is given as h nu. Now I can get this 13.6 out if I just do it like that. Final square. This gives me my formula as h nu 13.6 1 upon n final square minus 1 upon n initial square. And this way I can get the frequency of the emitted photon, and if I do it like hc by lambda, I'll put the mu as c upon lambda, I can get the wavelength of the photon emitted. So this is how we do it. Now once we have done it, let's come to another part of the chapter, another final part of the chapter. So I'm sorry, this part says, how did Bohr got this second postulate? The second postulate where he said that MVRN is going to be NH upon 2 pi. How did he got this thing? On what basis? So it was de Broglie who explained this. So there's a separate part in your NCRT, de Broglie's explanation of quantized angular momentum. How can we say that the angular momentum is quantized? This was explained by de Broglie, I think 10 years later after the Bohr's model came. So how is it? How he explained it? He said that if I have a nucleus, an electron is revolving around it. So electron is revolving around it. The electron is a particle. Though as you study the wave chapter, as we study wave optics, as you will be studying wave optics in future, electron has wave nature also. Yes. So इलेक्ट्रॉन का वेव नेचर भी है, और इलेक्ट्रॉन कौन सी वेव बनाता है? इलेक्ट्रॉन हैज़ अ वेव associated with it which is called as the matter wave. This was de Broglie's postulate. So what did he say? Lambda is equal to h by p for any particle which has the momentum p, or you can say which has this momentum mv. The wavelength associated with this particle can be given as lambda. So this was de Broglie's theorem. So if this is the case, if electron can be considered as a wave moving in an orbit, then the only wave which do not dissipate energy while moving between two boundaries are the standing waves, as you have studied in your grade 11. Yeah, the only please don't mind the diagram, I've just made it in one go. So what I'm saying is, the only waves which do not dissipate energy between two boundaries are the standing waves. The waves which are formed on guitar are the standing waves. The waves which are formed on the surface of sitar are also standing waves. And the waves which are formed on the tabla membrane, they are also standing waves. However, in the real life, you would have seen that these waves dissipate with time, lose energy and get settled. Like no more sound comes in. Okay, this is what we have seen in real life. But if we talk about an electron inside an atom and moving around it, then since it's a matter wave, as you'll study quantum mechanics further, you'll know that matter waves have the amplitude expressed in the form of probability. So they cannot dissipate themselves this way. They cannot get dissipated by the physical factors. It's a I would say theory. It's a theoretical concept. So the standing waves, when the electron is behaving like a standing wave and while moving in discrete orbits, the condition for this electron's position, that is Rn, is that 2 pi Rn has to be the multiple of wavelength of the electron, n lambda. And if that's the case, then this Rn has to be a multiple of n lambda upon 2 pi. Yeah. And if Rn is this, then if I'll substitute the value of lambda in this case, in this de Broglie's postulate, what I get? I get 2 pi Rn upon n as my lambda equal to h upon mv. And if I further take out this mv in the other side, I get mv Rn is equal to nh upon 2 pi. And here it goes. This is the postulate that Bohr was talking about. This is the condition that get fulfilled whenever you consider electron as a a standing wave moving in an orbit, in a discrete orbit, and having its wavelength, having its radius of the orbit as an integral multiple of lambda, its wavelength. So this is how de Broglie explained second postulate of Bohr's. I hope I'm clear. And whenever this comes in your exam, you have to have note all this mathematics here, and you have to mention that electron behaves like a matter wave and makes standing waves in discrete orbits. And that's how you'll finish it off, and the topic would be covered. So I suppose we have covered most of the topics of this chapter. For your doubts, you can ask it further. And thank you. This chapter can be done only if you do the derivations by your hand. You see, they're not as typical. They're just like substituting one thing into another. So please be aware that you have to work it out on your own. Only then it will stick to your mind. Otherwise, it will you'll not be able to memorize all the formulas. One more thing is, the last topic is the limitations of the Bohr model. So limitations of Bohr's models involve, first thing, that he could not explain the difference in the relative intensities of emitted photons. For example, as Bohr could explain the line spectra in this way, that he mentioned that when electrons move from one orbit to another, it emits photons, and the photons have this energy h nu, which is given by E initial minus E final. You just found out the expression. Yeah. So the point is that he could explain the spectra, but what he could not explain is that why the spectra which was showing the different colors, it had one particular color, like for green it was showing a big thick line, whereas the red color was indicating a very thin line. Why there was this difference in the intensities that were being formed? Was there some preference for which photons would be falling back and which photons would not, which electrons would fall and which electrons won't fall? So based on that, this he could not explain. Moreover, the elements in the gaseous state give different spectra in the presence of magnetic field. For example, if you try to get the spectra of hydrogen, you pass on this you basically, I would say, you have this hydrogen tube which has hydrogen gas at very high temperature, at a very low pressure. You pass that light through a prism and you get a spectra on a screen. Yes, this is how we get the spectra on the screen. Now this spectra would be different if I would have an electric field placed near this beam, and if this spectra would further be different if I would have a magnetic field also placed here. So this was giving rise to more finer levels of lines in these in the spectra. Like in the real spectra, if I was getting just 3 lines, in the spectra that I obtain after placing electric field and magnetic field, I was getting more number of lines. So this was what he could not explain, and this is how the Bohr model need further refining, and it turned out in the form of Schrodinger's model. So you can study it later. That's not in your class 12th course, physics course. So thank you for the patience, and have a nice day. Take care.